Good morning, everybody. This is Ms. Benson, and we're starting second semester. I hope you're as excited as I am. We are entering chapter 12, 13, 14, and 15, which is really the heart of AP Chem. And this is a part where you're really going to need to do some more work, especially if you were kind of not doing as much as you should have first semester, because a lot of it was review. This is going to be all new stuff, and so you need to be making sure that you're keeping up with things. So today we're going to be starting with chapter 12, which is called Chemical Kinetics, and it's all going to be on reaction order and reaction rates. And if we take a look at certain things, like right now when you are eating some food, the reaction rate is going on in your stomach and in your body as to how quickly your body is able to decompose the food. And that is all going to be a reaction rate. You want some things are going to decompose, or they're going to have a reaction rate that's very quickly. Like if you've taken some caffeine, or if you've taken some sugars, that your body decomposes that very quickly, and that energy is consumed and it's also burned very quickly, and you might have a lull after that. Where if you eat something that's higher in protein and better vegetables and better for you, that energy lasts for a longer period of time. All has to do with reaction rates, and that's what this whole chapter is going to be about. Quite a bit of math in here. Hopefully not any difficult math. There's a little bit of calculus here, but we will be skipping over some of those parts. So, Chapter 12, Section 1, Reaction Rate. Reaction rate is the change in concentration of a reactant or product per unit time. Now, something that you need to make sure that you are getting used to is, remember the parentheses that I talked about, or brackets, I guess I should say, is that when you are talking about concentration, that your book is going to put everything in a bracket. Remember that concentration equals molarity, and that's equal to moles over a liter. So we are talking about the molarity of the reactant or product over time. And so we are talking about our reaction rate. So our reaction rate is going to be equal to our concentration, and if we call A as our reactant or product, and we are going to say the concentration of one substance is reducing over time of the reaction or concentration of the second substance over our change in time. Now, because we can say that our product is going to be obviously a result of what our reactant is. And so if our reactant is going to be decreasing, it's going to be consumed as the reaction goes along, then they have always thrown this negative sign out in front, showing that it's decreasing, that our change in our reactant over the change in time. Now, we are going to be shortcutting this a little bit, and we'll leave this for quant chemistry when you get there. But we are going to always focus on our reactants. Our reactants are going to be decreasing in our buildup of our products. I think you can probably imagine that there's going to be some equations where our products are going to build up so much that they actually come back and affect the rate of our reactant decreasing. We are going to negate that part, and we're just going to simply focus on our reactants that are going to be decreasing over time. Okay, so instantaneous rate, the slope of a line tangent to the curve at some point. So if I'm going to say again that our slope is equal to our change in y over our change in x, which is something all of you have had for many years now, we can go ahead and take a look at the stoichiometry of our reactions. So if we take a look at something really simple like nitrogen dioxide. So we're going to write down nitrogen dioxide. We know that that is in the gaseous form, and when that decomposes, I'm going to get 2 moles of nitrogen monoxide in the gaseous form, and I'm going to get oxygen gas as another product. So as we take a look at this, if I'm taking a look at my change in rate, if I was asked to talk about my rate of consumption versus my rate of production, I should be able to say, yes, this is going to be decreasing as time goes by. It is the concentration of my NO2 over my change in concentration, or my change in time. And that's going to build up on this side, so I'm going to have a positive sign over here, that my change in my concentration of my nitrogen oxide gas, monoxide gas, over my change in time is also going to be equal to twice. I have to keep in mind that it's my rate here, my change in my concentration of my oxygen over my change in time. Well, how did I know that this was 2 here? Well, if I take a look here in the way that I wrote it, I have 2 moles of nitrogen, sorry, should be dioxide right here, forgot my 2, nitrogen dioxide to 2 moles of nitrogen monoxide. Well, the ratios are the same, 2 to 2, so the amount that the rate is changing should be increasing over here. However, because I only have 1 mole of this, what is this? I'm not sure what that is. So if I only have 1 mole of this, you can see that my rate of production are used or produced 2 times as fast as my oxygen over here. These are the things that we're going to start looking at and we're actually going to calculate. So again, stoichiometry plays a big part in all of this. Alright, so moving along to the next page, you guys have the same picture that is in your book. And you can see it goes along with the equation that I just wrote. Should make sense to you that this is my reactant right here, and so this should be decreasing as I move on in time. And so our XY axes here, hidden way down here, I have my concentration over time. And so my nitrogen dioxide gas is going to be decreasing as I march along time. Here are my 2 products that I wrote, my nitrogen monoxide and my oxygen, and you guys can see that that is going to be increasing as time passes. I'm producing a product. That should make sense to you. And it also should make sense to you that my oxygen is half as fast due to the coefficients that I have here. So if I were to take a look and I was just going to write our rate law, our rate expression. If you were asked to write your rate expression for this one, it would be, it's decreasing. Remember, we are paying attention to our reactants. So our reactant is nitrogen dioxide gas over the change in time. Again, we can see that that negative sign means that it is reducing as time is going by. And then the next chart that we have on here that also follows along with your book, you can see that if I look at the values experimentally, you can see that it says concentration of reactants and products as a function of time. It's the same equation that I had written there before, products over reactants there. And time's going by in second intervals, and you can see that my concentration here of my reactants is decreasing, and this is actually increasing, and you can see that we experimentally could take a look and do a mathematical difference of those rates. So here I have another table here. The average rate, you can see again when it says moles per liter, again we're talking about concentration, so molarity over time. So how much is that changing? Decomposition, you should have recognized that that was a decomposition reaction as a function of time. So again, it's talking about its change in rate in this time period. You can see that it is decreasing. You should see that the rate is not decreasing constantly, but it decreases with time. So we need to calculate the slopes, and we need to calculate the tangent to the curves to be able to compare. Well, again, we're going to shortcut that just a little bit so that we can make sense of all of these crazy numbers. All right, so section 12.2, so we have rate laws introduction. Rates of reaction must be considered before the reverse reaction becomes significant. So that's what I've already mentioned, that we are basically just going to be looking at our reactants, not worrying about our products, because then it becomes a very difficult problem to solve. All right, so the initial rates are studied before products can accumulate and affect anything that is going on. So this again is going to be the rates of our reactants. You can see that we have it decreasing, our change in concentration over time, and then we're talking about a constant now. So K is going to stand for rate constant, and that is going to be in molarity over time. And then we have N right here, which you can see right here, and this is going to be, we're going to talk about a first order, zero order actually, first order, second order, third order reactants. And this is just, like I said, it's just going to be an order of reactants. We're going to talk about how to find that experimentally. So it's the order of the reactants refers to the concentration of the reactants. And so we'll be taking a look at our experimental data to be able to determine this. So I said experimental more than once. You need to pay attention that this right here is an experimental value. We can only do this experimentally. And then at times we'll be giving you values so that obviously the experiment has already been done for you. So types of rate laws, there's a little summary on box 534 in your yellow box. It talks about the differential rate law and the integrated rate law. If you are in calculus, those terms mean something to you. They're always related. We can always relate them to our reactants. So we're not really going to differentiate between either of these rate laws. We're just going to use them. And the reason that we need to use them is that I think by now you can understand that most chemical reactions do not happen just once. It is a series of steps, it's a series of reactions, kind of think of Hess's law, and that we need to understand which reaction is slowing it down, which reaction is the slowest step. And you can take a look at your body. It takes 21 chemical reactions to break down any food that you are eating. Well, we could take a look at the reaction rates of each of those chemical reactions and figure out which one is the slowest one and figure out the different rate of that. It's going to be determined by the slowest step, and that's what we're going to be focusing on. Okay, so I think I'm going to stop right there for this first pod lesson, and hope you guys have an awesome day.